Hey guys, this video is going to be on implicit differentiation. So most of the time we're usually given functions that are defined explicitly, such as y equals x plus 2. Now this function is explicitly defined. We know exactly what the function is of y in terms of x. So let's say we wanted to find the derivative of this. We could easily find dy dx as just 1 at any point down the line. But let's say, for example, that we're given something a little more complex, such as x squared plus y squared equals 25. And we're asked to find the slope at point 3, negative 4. Now, this could be done explicitly. We could solve for y and take the derivative, and then plug in our points 3 and negative 4. However, this would be kind of a waste of time, as there's a faster way to do this. So let's say we were to solve this the regular way. So first we would have to isolate y squared. We would get that y squared is equal to 25 minus x squared. And we would take the square root of both sides. So we would get that y is equal to plus or minus the square root of 25 minus x squared. Now, since we know that we're looking at point 3, negative 4, we know that that's in the bottom half of our coordinate system. So we know it's not the positive one, and it's actually the negative one, which is the bottom half of our circle, which is a semicircle on the bottom. So we know that y is negative square root 25 minus x squared. So now if we want to find dy dx, we can say that it is negative 1/2 times 25 minus x squared to the negative 1/2. And don't forget chain rule, so times negative 2x. Now this is equal to, this leaves us with x over the square root of 25 minus x squared. And we want to find the slope at point 3, negative 4. So if you plug those points back in, we're left with 3 over the square root of 25 minus 9, which is basically 3 over square root of 16, which leaves us with 3/4, which is our final answer. Now that's one way to do this problem. However, as you can see, that took a decent amount of time. There's a faster way to do this problem you could do that by using implicit differentiation. So what implicit differentiation really is if a function is given to us, some function y, it can be written implicitly as a function of x. So for example, this right here, what we used before, it's not explicitly given to us as a function of x. We're not given y is equal to something. We're given x squared plus y squared equals 25. However, we can take the derivative of the whole thing, each term by term, using all our derivative rules such as chain rule, product rule, and all those will still apply, except we take it with respect to x. So we can try this problem now using implicit differentiation. So let's see how that would work in this case. So we start out with x squared plus y squared equals 25. Now, since we're taking the derivative of everything with respect to x, the derivative of x squared will just give us 2x. Now the derivative plus the derivative of y squared, but since it's with respect to x, it would be 2y. Now since there's chain rule, we have to remember to multiply this by dy dx. And our 25 will just leave us with 0. So now, all we have to do to find dy by dx is isolated. So we know that 2y times dy dx equals negative 2x. And we can say that dy by dx equals negative x over y. Now we can just plug in the points that were given, 3, negative 4. So when we do that, we're left with negative 3 over negative 4, or just 3/4. So we get the same answer either way. And obviously, this took a lot less time than it did before when we were trying to solve it explicitly. So that was one example. Now let's try a couple more examples that are AP problems. So this question was given on an AP, it was part of an AP free response question. The problem started out as 2y cubed plus 6x squared y minus 12x squared plus 6y is equal to 1. Now that's given to us, and the first part of this problem was to find dy by dx. So let's start by doing that. So we do the same thing as before. We take the derivative of each term with respect to x. So this 2y cubed would become 6y squared, but don't forget chain rule, so times dy dx. This 6x squared would become, now for this we have to remember to use product rule. So it would become 12xy plus 6x squared dy by dx. Now this negative 12x squared would just leave us with negative 24x. 6y would leave us with 6 dy dx. And of course the 1 will just leave us with 0. So now what we want to do is we want to pair up the like terms, solve for dy dx. So we can say 6y squared dy dx plus 6x squared dy dx plus 6 dy dx is equal to 24x minus 12xy. All these coefficients are divisible by 6, so we can cancel these out. This will leave us with 4, this will leave us with 2. So we can factor out a dy by dx here. As all of these have a dy by dx term. So dy by dx times x squared plus y squared plus 1 equals 4x minus 2xy. And finally, we can do the last step, just divide, and we're left with dy by dx is equal to 4x minus 2xy over x squared plus y squared plus 1. That's our final answer. So let's go through one more question. So this next question was actually a multiple choice question that showed up on a previous exam. The question was sine of x is equal to e to the y. Now this question is a little harder, as we have to do a little more substitution than usual. So we can start by taking the derivative of each term implicitly. So we're left with the derivative of sine x is cosine of x. and we know that and this is equal to the derivative of this side, and the derivative of e to the something is just e to the something. But we have to remember chain rule, so it would be e to the y times dy by dx. Now we can isolate dy by dx, and we would say that dy by dx equals cosine x over e to the y. So if we actually looked at the answer choices on this question, this is not there. The AP wants us to do a little more with this question. So instead of just leaving it like this, what we can do is we can solve for y using this equation, what's given to us. So we know that e to the y is equal to sine of x. So if we take the natural log of both sides, we can say that ln e to the y equals ln sine of x. So this ln and this e would cancel, and we're left with y equals ln times sine of x. Now we can substitute this back in to y here, and that would leave us with dy by dx being equal to cosine x over e to the ln sine x. Now we know with our exponent rules, e raised to the natural log of something would just leave us with this sine of x. So we can simplify a little bit more and say that dy by dx is equal to cosine x over sine x, which is just cotangent of x. And that's our final answer. So that was implicit differentiation, and hopefully this video helped. Thanks.